Okay, in Module 8 we are going to do a unit on trigonometry. So trigonometry is something that you should have done in geometry in previous coursework. So in Section 1 we're just going to kind of review some of the basics of trigonometry and right triangle trigonometry. So here you see I have drawn a right triangle. That has one right angle and then two acute angles. If you remember, all of the angles in a triangle add up to 180. So in a triangle we have a couple different parts. One part is the hypotenuse. So the hypotenuse is always the longest side and it's always across from the 90-degree angle. So if I look at this triangle up here, ACB, then this would be the hypotenuse. It's the longest side, and it is across from the 90. Now we also have what's called the opposite and adjacent side. Now if I say what side is opposite, it typically boils down to opposite of what? So we have two angles. We have this angle B, which kind of got cut off. So if I look at angle B, the side that is opposite of angle B would be this AC. So this would be opposite of angle B. Okay? So when we say opposite side, we mean the side across from an acute angle. So it's the side across from one of the smaller angles that's not the 90. Okay? When we talk about adjacent side, that would be just the side next to it. So if I look at angle B, the side next to it, well, there's two sides next to it. It's either AB or BC, but AB was already the hypotenuse. So this side is what we call the adjacent of angle B. So the adjacent side is the side next to an acute angle. Now, that's the sides if I did B. If I were to pick a different angle, let's say I picked angle A to deal with. Well, if I was dealing with angle A, then this side would be opposite of A, and this side would be adjacent of A. So it just depends what angle you're talking about, which one of the two acute angles you're talking about, to set up your trig ratios. Now, trig ratios really are simply just taking these different sides, the opposite, adjacent, and hypotenuse, and we're simply dividing them by each other. So what it gives us is it gives us a ratio for any type of triangle that has a certain set of angles. So if I look at this triangle here, where I have said angle theta, well, this is very common trigonometric notation, so if you haven't seen this before, when I put the Greek letter theta in the corner, this means this is the angle I'm dealing with. Like I could deal with either of the acute angles, but when I have the theta there, that means that's the one I'm dealing with. So that would make the longest side hypotenuse, it would make this side the opposite and this side the adjacent. So the neat thing about trigonometry is if I look at any triangle that has an angle theta, any right triangle has an angle theta. It could be a big triangle or a little small triangle like this that has those same angles. The ratio of the sides is always the same. Meaning if I divide, say, the opposite divided by the hypotenuse in this big one, and I divide the opposite and hypotenuse in the small one, I will get the same number. And we call these trig ratios. There are actually 6 trig ratios, 3 which you probably learned in geometry, and then 3 new ones where we're going to talk about here today. So the sine of angle theta is the opposite side divided by the hypotenuse. The cosine is the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. This is sometimes referred to by the moniker of SOHCAHTOA, which says sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So these first 3 are ratios that you should know and you should have seen from geometry. The last three are new ones, but really all they are is just the flips of the first three we have. So the first one we see is cosecant, which is abbreviated CSC. So the cosecant of an angle is just the flip of sine, so instead of being opposite over hypotenuse, the cosecant is hypotenuse over opposite. This relationship between sine and cosecant is called reciprocal relationship because they're just flips. Secant is the reciprocal of cosine. So if I flip the cosine ratio, which is adjacent over hypotenuse, I can get the secant relationship. And similarly with tangent and cotangent, instead of opposite over adjacent, is it adjacent over opposite? So we're really going to practice setting up these ratios in some right triangles. So here I wanted to find the 6 trigonometric ratios of the triangle given. Okay. So here is my angle theta. So the first thing I would do is I would define what my sides are. This is definitely the hypotenuse. It's the longest side. It's across from the 90. Now if I think what side is across from theta, that would be side 10. So this is the opposite side to theta because we're dealing with angle theta. And then that's going to make 24 the adjacent. So once we have all the sides defined, and we know what all the sides are, 10, 24, and 10, 26, we just basically plug in numbers. So if you remember, we said sine was opposite over hypotenuse. So that would be 10 over 24, which I want to reduce, that is going to be, or excuse me, 10 over 26, because the hypotenuse is 26. So if I reduce that, that's going to be 5 over 13. The cosine is adjacent over hypotenuse, that's our ca. So that's adjacent over hypotenuse, so that's 24 over 26. So reducing 24 over 26 will give us 12/13. And then tangent is the opposite over adjacent. So the opposite side would be 10, and the adjacent would be 24. So 10 over 24 will reduce to 5/12. So these are all things you should have done in geometry. So these new ratios, we could try to memorize them, but all I have to do is I know cosecant is the flip of sine. So instead of 5/13, it'll be 13 over 5. And I know secant is the flip of cosine, so it'll be 13 over 12. And cotangent is the flip of tangent, so it'll be 12 over 5. So remembering the sine, cosine, and tangent, and then knowing which one kind of is the flip of those, is actually really pretty simple. Now if we look at the next question, we're trying to find the 6 trig function values for angle A. So we're really talking about angle A. So when we define our opposite, adjacent, and all that, we're going to be really looking at angle A. Now what you also notice in this problem is we have a measurement for BC and for AC, but we do not have one for AB. So if we think about this, we know 60 is the hypotenuse, it's across from the 90. The side across from angle A would be this 50, so that's the opposite. So the adjacent is the other side next to it, which we don't have a value on. But since it's a right triangle, you may remember the Pythagorean Theorem, which states a squared plus b squared equals c squared. The only caveat on this theorem is that c squared must be the hypotenuse. So if I plug these values in, a squared and b squared really could be either of the legs, so maybe I'll make this one 60 squared, plus b squared, which is the other leg. Scratch that. 60 is the hypotenuse. So we'll make it 50 squared plus b squared equals 60 squared. Because I always want this hypotenuse to be the c in our Pythagorean theorem. So 50 times 50 is 2500 plus b squared. 60 times 60 is 3600. So I can subtract 2500 from both sides. So b squared is going to equal 1100. And then I'll simply take the square root of both sides. So b, which is this adjacent side, is going to be the square root of 1100. Or if I simplify that, I know b is going to be 10 times the square root of 11. And you could do that by breaking it down. If you remember how we took 1100, we could go 111, and that's a prime, and this is 10 and 10. So I have a group of 10s that come out with an 11 left. That's how I got 10 root 11. So this side is 10 square root 11. So if I start to put these values in, now that I have all the values for my triangle, the sine is the opposite over hypotenuse, so that's 50 over 60, which can reduce to 5, 6. Well, once I know that, well, I also know the cosecant, because that's just the flip of that, so that's 6 over 5. So now I've got my sine and my cosecant. My cosine is the adjacent over hypotenuse, so that's going to be 10 square root 11 over 60. But I can reduce this 10 over 60 to be 1/6. So this would just be the square root of 11 over 6. The secant would just be the flip of that, which would be 6 over the square root of 11. Now the 6 over square root of 11, it's a fine answer and it is the correct answer, but sometimes we will like to write that without a root on the bottom, which is called rationalizing, which we covered in the first semester. But if you remember how we do that, all I do is multiply the top and bottom by the same square root, in this case 11. So that'll give me 6 square root of 11 on the top, and the square root of 11 times square root of 11 would just be the square root of 121, which is just 11. So this value, 6 over square root of 11, and this value, 6 square root of 11 over 11, is the same number. It's just the second one has no square root on the bottom, and that is kind of a more proper, rigid mathematical way to write it. Not incorrect to write it the other way, just a little different. So the tangent of A is opposite over adjacent. So if I do the opposite over adjacent, that's 50 over 10 square root of 11, which if I reduce 5 and 10 will give me, or 50 and 10 will give me 5 over square root of 11, which I know the cotangent then is going to be the square root of 11 over 5. And again, if I want to get rid of the square root of 11 on the bottom here, I could. We'll just make this 5 square root of 11 over 11. And again, both very good answers. 5 over root 11 and 5 root 11 over 11 are the same number. You can put them both in a calculator and figure it out. But they would give you the same decimal. So let's look at an extension of this where we can actually find trig ratios based on one given trig ratio. So this example says if the sine of theta equals 2/3, find the values for the other 5 trig ratios. So really what I want to find here is I want to find out what is the cosine of the angle, because I know the sine is 2/3. What is the tangent of the angle? What is the cosecant of the angle? What is the secant of the angle? What is the cotangent of the angle? So really I just want to find the first 3 and then flip them to find the last 3. Well, since I really don't have a triangle here to work with, the first thing I'd do in this is I would draw a triangle. So I'm going to draw a right triangle. And I know this is going to have angle theta. Now the only thing I know about this triangle is I know its sine value, the sine of angle theta, is equal to 2 over 3. Well, if you remember what sine is the opposite over the hypotenuse. So in this triangle, the hypotenuse is the longest side across from the 90, that would be 3. So this side would be 3. The other side, the opposite side of theta, would be this side across, and that is 2. So because I know this triangle has a sine of 2/3, I know its opposite side and its hypotenuse, because the sine ratio is sine is opposite over hypotenuse. That's why it's so important to know what those ratios are. I can then find the other side using Pythagorean Theorem. So 2 squared plus the other side squared, we'll call it x for now, equals the hypotenuse squared. So that's 4 plus x squared equals 9. I'll subtract 4, so x squared will equal 5, and then I would take the square root. So x, which is this unknown side, is the square root of 5. So now everything works just like it did before. We know this is the hypotenuse. We know this is the opposite, because that's how I set up my triangle. And so this is, of course, the adjacent. So cosine is adjacent over hypotenuse. Remember, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So adjacent over hypotenuse is going to be square root of 5 over 3. And the opposite over adjacent, this is not 20, this is opposite. I probably should make that more clear. So tangent is the opposite over adjacent, so that's 2 over the square root of 5. And you could rationalize it, but I won't do that for this one. And then for the cosecant, secant, and cotangent, I'll just flip them. So cosecant would be 3 over 2. Secant would be 3 over the square root of 5. And cotangent would be the square root of 5 over 2. So the next one, very similar, says given the sine of theta equals square root of 5 over 4, find the exact values of secant and tangent. So we only want 2 of them in this case. Now, there's nothing that says you can't find them all and then just pick out the ones you want. And I think it's probably easier to just find them all and then just pick out the ones you want. So cosecant, secant of theta, and cotangent of theta. So I'm going to draw another triangle with a theta, and it doesn't matter where I put the theta, I'm just going to put it in this corner. Sine is still opposite over hypotenuse, so the 4 is the hypotenuse, and the opposite side is square root of 5. So this works just very similar to the one above, so I'm going to find the missing side by doing Pythagorean Theorem. So square root of 5 squared plus the missing side squared equals 4 squared. So the square root of 5 squared is just 5 plus x squared equals 16. I'll subtract 5, so x squared equals 11. I'll take the square root, so x equals the square root of 11. So this side down here is the square root of 11. So now remember, this was the opposite side, this was the hypotenuse, this is the adjacent side. So sine was square root of 5 over 4. Cosine is adjacent over hypotenuse, so that's square root of 11 over 4, which really wasn't one of the ones I was looking for, but that's okay. Tangent's opposite over adjacent, so that's square root of 5 over square root of 11. So that's one of the ones I was looking for. The other one I was looking for was secant, which is the flip of cosine, so that would be 4 over square root of 11. I could certainly find cosecant as well. That would be 4 divided by square root of 5. And cotangent would be square root of 11 over square root of 5. But I just really wanted those two in this problem. But finding extra really is never going to hurt you. Okay, our last one, really basically the same thing, except for in this case it gives us to us as decimal. So there's one little trick in this. So it says the cosine of angle beta. So we've been using theta, beta is another way to go, so I'll just put a little b or beta in the corner. Now cosine is adjacent over hypotenuse, and in this triangle, this is the hypotenuse, this is the opposite of beta, So this would be the adjacent. Now, cosine of 0.32 doesn't really have a fraction like adjacent over hypotenuse. So what I'll do is if we ever have this, we'll just put it over 1. So now my adjacent would be 0.32 and my hypotenuse would be 1. So I will find the opposite side in this case. But again, same Pythagorean theorem. 0.32 squared plus our unknown side squared equals 1 squared. So 0.32 squared is going to give me 0.1024 plus x squared equals 1. I'll then, of course, subtract 0.1024 to the other side. So that would give me 0.8976. And then I'll take the square root. So the square root of 0.8976 is going to give me 0.9474. If I wanted to round it, I certainly could. Maybe I just round this to 0.95 to make it have the same number of decimals as the other one, because this is some long irrational number. So now I've got my opposite, my adjacent, and my hypotenuse. I can set up any ratio I want. So it asks for the sine. So the sine I know is the opposite over the adjacent. So sine is going to be 0.95 divided by 1, or just 0.95. Now cotangent I know is the flip of tangent. Tangent is opposite over adjacent, so cotangent would be adjacent over opposite. So that would be 0.32 over 0.95. So really the key in this first section, just reviewing some of our basic trigonometry, know those ratios, know what side is opposite, adjacent, and hypotenuse, and just find your ratios.